Good morning, guys. Today we will be discussing concepts on shear. So, what is shear in terms of a beam analysis? So, from the determination of your load, shear, and moment diagram, the magnitude of shear force at each and every section of the beam must be taken into consideration when you are uh, designing a building, a beam as a whole. Okay, so for the requirement of the shear resistance of beam in the strength design criteria, so take note that this is your requirement which must be satisfied in order for your beam to be allowed to perform in terms of shear behavior. So your VBN, which is now your shear capacity, must always be greater or equal to your factored shear. Okay, where your shear capacity is your nominal shear multiplied by your reduction factor phi, which is 0.85. Uh, there is difficulty in assessing shear strength, and these are the reasons why uh, the shear behavior is really very hard to predict. But later on, you will notice that by simply understanding the behavior, so we can actually uh, formulate an equation so as to handle your shear capacity determination well, and come up with a satisfactory design in terms of safety. So these are now the reasons why shear is very difficult to assess. So first, shear seldom acts alone. So we cannot isolate the behavior of shear without uh, analyzing the other aspect of beam behavior, such as moment and maybe torsion later. Okay, so shear acts always with a lot of other behavioral characteristics, such as bending, torsion, uh, actual behavior, and a combination of these other behavioral characteristic that influences the difficulty in the assessment of shear strength. So number two is that the development of diagonal cracks are so complex. No, it produces a very extreme complex pattern, which will confuse many observers who are actually making some research and study regarding the behavior of beams in shear. So the third one is that shear behavior relies heavily on the material tensile strength of concrete, and since tension is also a very hard uh, parameter to assess, since it varies mainly from your compressive strength, which is also uh, is heterogeneous in terms of its value from one point to the other point along the beam, then in totality your shear assessment is really very difficult to observe. But again, as I have said, we will try to understand better how it works, such that the formula later can be interpreted correctly for us to be able to satisfactorily obtain a good design, and therefore a very safe design in shear can actually be expected. So for a typical beam here, we have actually shown the crack pattern. Okay, so you call this now the crack pattern, wherein shear varies from one point of the beam to the other. Okay, so if you will look at the crack pattern now, you will notice that the crack, in terms of its inclination or the angle theta, or maybe alpha, as we are going to use later, uh, the value of alpha seems to be increasing, no, in terms of the magnitude, and at the midpoint or the midspan of the beam, it's almost 90 degrees. Okay, so alpha here is almost vertical at the midspan, while alpha here is more or less 30 to 45 degrees. Okay, so this observation can be attributed to the fact that the flexure and shear combined will create a biaxial state of stress. Okay, and the cracks which are formed are coming from the principal stresses, tensile stresses, which actually happens only when uh, the stresses exceeds the tensile strength of your concrete. So for example, if we are going to look into the free body diagram of a beam, in terms of the load, shear, and bending moment. Okay, so if this is now your beam load diagram, we have the shear diagram and the moment diagram. Okay, so we will notice that at this point, somewhere very near to the support, your crack pattern, which is at point 1, is given by this biaxial state of stress. So you call this now 1, 2, 3 the biaxial state of stress. So when you say biaxial, there are two axes. One is vertical and the other is horizontal. Okay. So shear stresses are just like frictional stresses, which are at the surface. No, it tends to slide the surface. It tends to slice the surface or to cut the surface into two, such that this V here corresponds now to your shear stresses, which if we will look into the concept of equilibrium, this shear force here must be equal to this shear force when you sum up forces horizontal. Okay, and also this force here, which is also the shear V, must be in equilibrium with this shear force here, such that if we take the moment couple, uh, using the two couple, we can sum up the summation moment about, okay, let's say the center of this uh, square element will be 0. Okay, so because this is v times the distance here and v times the distance there, will create now a moment couple which are equal in magnitude and opposite in direction. Okay, so if you're going to look into this free body diagram, the resultant of these forces here, this force here and this force here, will tend to pull, okay, your your element, your square element, going upward to the left, and this will tend to pull the element going downward to the right, such that your resulting crack will simply be perpendicular, almost perpendicular to the direction to which this resultant force is actually pulling. Okay, that's why your crack here, if you will notice, is almost more or less 45 degrees there, although it's not accurately like that because of some influencing factor, but this can be very near to 45 degrees. Okay, for the second biaxial element 2, you will notice that there is now a flexural resistance that is horizontal in nature, which is pulling the cubical, or sorry, the square element uh, laterally or horizontally, such that your tendency for the pull will be on a direction which is slightly flatter. The slope is flatter than the slope of this. Okay, so this will now be pulled a little bit flatter like this because of the force that will make your resultant here a little bit flat, such that your crack now will, if you are going to look at the extension of this axis, so the crack will now be perpendicular, a little bit uh, vertical. Okay, so this will be perpendicular or 90 degrees with the axis to which this pulling force, tensile force, is pulling the square element, such that your crack now has an alpha which is greater than 45 degrees. Okay, so your alpha here will be bigger than 45 degrees until such time when the flexural stress or the bending stress at the middle is a maximum. You will notice that this will be almost zero when it is very near to the midspan, and therefore your flexural stress is a maximum at this point, such that your crack will be almost vertical. Okay, so 90 degrees. So the pattern of cracks now, the behavior of the crack, of the beam rather, can be seen uh, by observing the crack pattern. Okay, so the crack starts from more or less 45, then it goes higher, higher, higher until it reaches almost a vertical crack there. And this concept that I now discuss will give us some indication of the orientation of the crack and the different section, but still we cannot predict yet the strength of the beam because these are elastic concepts which does not fit very well in consideration of the inelastic concepts. So to continue, what are now the types of cracks? So we have what you call the flexural shear crack. Okay. The second is the web shear crack, and the third is the secondary crack. Okay, so as defined here in the lecture, the flexural shear crack is simply a diagonal crack originating and extending from the previously existing flexural crack. So the initiative in terms of cracking is actually begins from flexural crack. Okay, and then it will continue to crack in a diagonal pattern, which will be eventually uh, be a shear crack failure. Okay, so the meaning of that is that when you have now a part of the beam here, your crack originates from a flexural crack, a vertical crack, and then after the vertical crack there will be your shear crack. Okay, so this vertical crack here is your flexural crack, and this diagonal crack here is your shear crack. Okay, shear cracks are sometimes called diagonal cracks. Okay, for your web shear crack pattern, from the word itself, there are no flexural crack in the beams. Okay, and these are very evident on I-beams. Okay, so if you have a section, the section of beam is an I-beam like this, like those which are used in bridges, the pre-stress precast girders. Your crack pattern of the beam, if you will look at the longitudinal uh, view, okay, so the cracks will not be initiated by flexure, but rather it will start from a shear crack like this, because the width of the beam here is smaller than the width of the beam at the flange. Okay, so this is BW is less than BF there, so your crack will be initiated so at this point, and you call this crack your web shear crack. Okay, for your secondary cracks, these are no longer initiated by flexure and shear. These are cause of secondary, meaning to say these are the consequences of the flexure and the shear crack that develop on the entirety of the beam, in which your reinforcement are affected. No, I will show you later how these secondary crack uh, are uh, are observed when we go to the real analysis, the actual analysis of shear in beams. For the shear transfer mechanisms, we have actually five uh, important considerations on how the shear is transferred from one part of the beam to the other. Of course, the fifth here is not an ordinary beam. It does not happen on ordinary beams, but rather this happens on deep beams. Okay, so we will be considering this in a separate as a separate topic if we still have time on it. Okay. Okay, so let's focus more on this four. If you will notice, I have here a figure in which your VZ, VA, VD, VS are actually shown. No, so this is now your VZ. So your VZ is due to the uncracked concrete. So this portion here is uncracked. For VA, that is due to aggregate interlock. So if you have some aggregates here, you call this uh, aggregate shear cracks. Okay. And for VD, you see a dowel here. So this dowel here is actually your flexural reinforcement. No, this is flexural tensile reinforcement, which contributes also to your mechanism. And your VS, which is this vertical here, which is contributed by your stirrups. Okay, so for your VC and crack section, for your VA, this is the aggregate. For your VD, this is the flexural tensile reinforcement. And for the VS, you have the stirrups, or what you call also as your web reinforcement. So this is another term for stirrups. And the total uh, shear that is expected on the beam to resist the actual shear force is simply the sum of the four without the arc action, because this is a different topic. Okay, and you will notice that VC, VA, and VD are actually attributed to the concrete contribution. Okay, so this is for the concrete contribution, although this is a dowel, is still on the concrete, consider the concrete part of the mechanism, and your dowel here, sorry, your S here is now your stirrup contribution. Okay, so stirrup and concrete contribution. So you remember that, no? Your total V is simply the contribution of your concrete and the contribution of your stirrup. Okay, let's talk on some concepts on shear span, maybe after a short break. So I will cut my lecture here to accommodate some concerns if there are any. Okay, so I'll see you on the next video.